Okay, so our topics for today will be quite few. We're going to continue from last lecture and continue talking about metabolic engineering, and we're going to introduce the OPNOC framework, which is a bit more of an advanced tool that is quite powerful in terms of finding metabolic engineering strategies relative to this more simplistic approach that we talked about last time. But it also comes with some drawbacks. Um, as an auxiliary topic, we're going to talk a little bit about production envelopes, which is actually something we discreetly introduced last time, but we didn't really specify it by name and we didn't talk about them as much in depth as maybe we could have. So we're going to revisit them a little bit and talk about how we can compute them and why they are useful to us in particular. So when we're doing metabolic engineering, our problem is generally of this form here. So what we're trying to do is we have an organism that we want to manipulate, we want to tweak it so that it satisfies our objective. We have something we want that maybe the cell can help us with, and we want to make sure that it does. And so typically that objective will be the secretion of a given metabolite, right? We can't force a cell to do our dishes or anything like that, but we can maybe have it produce some sort of compound that's useful to us, say some sort of antibiotic. And so we will have one objective, which is a flux through a given reaction, typically a secretion flux for an exchange reaction, right? And what we want the cell to do is we want it to maximize that. The thing is that the cell doesn't know that we want that to be maximized, and it's not going to listen to us in any case. The cell has its own objectives. What the cell wants to do is typically it wants to grow. So it will have an objective on its own, and that's going to be growth. And what we want to identify is we want to identify over a set of gene knockouts typically, or some other, for that matter, nutrient manipulation, a set of mutants for which the objective is the highest when the cell is maximizing its own objective. As a linear program, if we're going to be a little bit more mathematically formal about it, it looks something like this. So we have our inner problem, which is a standard FBA problem, which is what the cell is sort of trying to solve. And then we will have to do a bunch of solutions for that in order to identify the optimum value here that satisfies our objective. And the way that we saw that we could do that in the last lecture earlier this week was that we can simply perform a bunch of knockouts. We can do, for instance, like a single gene knockout for every gene in our organism, find the solution to this inner problem, and then find which of those solutions has the highest flux through our objective. The problem with this is that this sort of brute force two-level optimization isn't feasible for higher order knockouts. We can do maybe a single knockout. We can maybe even do double knockouts, but for each additional gene we want to knock out, if we want to exhaustively search strategies in this way, we have to do an exponentially increasing number of tests, essentially, right? If we have 100 genes, single knockouts, that's 100 tests. Double knockout is 10,000, triple knockout is 1,000,000. And if we want to identify maybe a strategy that involves 5 or 6 knockouts, because that might be what's necessary to really get the best result, that is just not going to be feasible in any respectable amount of time. So the question we have then is, can we find some sort of approach that allows us to identify efficient strategies where we are doing much higher order knockouts than what we can do by this original simple approach that we talked about earlier? And that is where OPNOC was developed. So the principle of OPNOC is that it converts our linear programming problems in a more tractable way. So we have our two-level optimization. It has an inner problem, which is the FBA problem, and the outer problem, which is the OpNoc. So what we can do to begin with is that from linear algebra and linear programming, we know that a linear program in this form here can be reformulated into a dual. The exact steps and how you convert the primal to the dual are not part of this course. You're not expected to be able to do this sort of conversion from this to this. That is fine. However, what we do know is that these two problems can be are equivalent to each other. So essentially, what we have here is, for the primal, we have an original objective function and an original set of constraints. The dual will involve a new objective function and a new set of constraints, but the variables going in are the same, right? The fluxes here are the same. And what this dual and primal formalism for linear programming entails is that any solution, the optimal solution to this dual problem, is the same as the optimal solution to the primal problem. And what that means is that the optimal solution must satisfy both this and this at the same time. So what we can do is, instead of solving this inner problem here by a standard linear programming solution, what we can do is, instead of solving this inner and then the outer, we only have a single level linear programming problem, or not linear, but a programming problem. Oh, it is linear, but it's not a standard linear program because it has some integer constraints. But nonetheless, we have a linear programming problem, a single optimization problem, where here we only have this outer bound, and now instead of our inner element here being an optimization problem, what we do is we just merge our constraints. So here, since the optimal to this and the optimum of this are the same for the objective functions, we can say that these two have to be equal, and similarly all of these constraints have to be satisfied and all of these have to be satisfied. When we merge that, instead of having our optimization problem, we just have, or instead of having a double optimization problem, we just have this outermost and a bunch of constraints. So if we see here, this upper constraint here corresponds to the fact that the objective of the primal and the dual have to be the same. And all these constraints here are either constraints from the primal, such as this here, the stoichiometric matrix, which we see here, glucose uptake, which we see here, ATP maintenance being satisfied, which we see here. That's on one hand, and then we also have these stoichiometric constraints from the dual, which are these. So now, instead of having this double nested problem, we only have a single level problem with a somewhat more complicated set of constraints inside it. And even though these constraints are more complicated, this single level problem has far fewer combinations in it and becomes quite a lot faster to solve than what we would get by doing it on our original double level optimization approach. So what this allows us is that this allows us to have higher values of k in a given amount of time. For a given runtime on our computer, we can have higher values of k in feasible, and then search our possible knockout strategies that much faster. And that is the main benefit of OpNock. It allows us to do this sort of two-level optimization. That is in practice what we're doing, but rewriting it as a single level problem. Even though that single level problem is slower than just the standard FBA problem, partially because of the knockouts changing. Like, so not all of these constraints here are standard constraints like we have in linear programming we looked at earlier. Particularly here, because these values here, y, have to be fixed integer values, and as it happens, optimizing individual or optimizing these variables when the numbers can only assume integer values is a lot harder. This is, again, quite a bit outside the scope of TBT 4165 as a whole. But integer linear programming, or integer programming, is what we call NP, or I think NP complete problems that are very tricky to solve for various reasons. But nonetheless, it is still faster than doing it twice over. And that allows us to try more advanced knockout strategies, quintuple, sextuple knockouts, while still keeping a reasonable runtime along the order of, say, maybe at most a few hours. The problem with this is that it has one major drawback, and is if we look at this this optimization problem, it's not always going to. It's going to. The solution that this returns might not tell us the whole story. Specifically, when we optimize this, so OpNock is going to give us the solution to this problem. It's going to give the highest value we can get for a bioengineering objective, while the cell is trying to maximize its own cellular objective. And so what it will do is it will give us the best case result according to our bioengineering objective. And as we talked about last time, identifying the best case is not necessarily always that useful to us. Because if we look at this schematic here, so here we have a plot of our x-axis is biomass production and y-axis is the lactate production, which is going to be our engineering objective, right? And so this thick line here, that is the wild type. We see that in the wild type, the faster it grows, the less lactate it secretes. And that is not compatible with our desires. And so if we feed this model into OpNock, it's going to identify certain mutants, and it's going to identify their optimal it's going to identify their, like, an optimal biomass production, and for that optimal biomass production, it's going to identify the optimal lactate production. So, for instance, here, this is actually a quite valid mutant. We see that it grows quite fast. It doesn't produce quite as much lactate in its optimum as the others. It produces only about 2/3, but it grows almost 3 times as fast. So that can be quite desirable, really, because the net production would be higher, since this produces at 2/3 of the speed, but grows 3 times faster. The effective final production rate of our desired metabolite would actually be twice as high as for these. Meanwhile, both of these here can produce quite a high lactate amounts per gram dry weight. But if we look at this middle mutant here, we have a problem, because the cell will itself, our mutant will try to be somewhere along the line. So this line here, or this line here, and specifically is going to be at that point or any of the points that is the furthest to the right. And for this one, it's fine, because here we only have one solution, and that involves a very acceptable level of lactate growth. Similarly, lactate production. Similarly, here on this one, its optimal growth involves it's a single point and involves a respectable amount of lactate production. with this middle one here, uh, we we could theoretically have the mutant behave so that it produces, so that it grows optimally because that's what it wants to do, but also doesn't produce any lactate because it doesn't care about producing lactate. It cares about growth. We're the ones who care about it producing lactate. And so this mutant B here is not really a great mutant for us. And that's a problem because if we just do opnock, all it will return to us is this point. It will tell us what the mutant is. It's going to give us this point with a biomass production and a lactate production. And we're not going to be able to tell right off the bat that this is a valid approach, or this is a valid solution for the cell as well, and a possible outcome of our mutant. So how do we deal with this? Well, we use this sort of a plot. This is what we call a phenotype phase plane. Sorry, not a phenotype phase plane. A production envelope. Yeah, actually, before we go over to production envelopes, we can also talk about another problem that we can have from this opnock is that if you look at our wild type like this, we could theoretically identify a mutant that produces a very high amount of lactate and at the same time doesn't grow at all. And that would be a problem to us because we need a certain amount of growth for our cell to be viable. And in order to satisfy that, we have in our optimization problem, we have this following constraint here, that the V biomass has to be higher than a certain target biomass. If you didn't have this constraint, then you could sort of identify mutants that produce a great amount of our metabolic objective, but doesn't grow at a rate that means that it will actually effectively produce anything. So therefore we need to have a cutoff. And so here, maybe the cutoff would be set here, for instance, or this line and here would be a decent point, and so we would only identify these knockout strategies that grow at least that well. But we have to make a choice. And the problem in making such a choice is that often we can miss an opportunity. If we look, for instance, if we had a cell where the wild type looks like this, and we specify a given biomass requirement, this here, we might miss out on some very useful strategies here that would have much higher values for engineering objective and and not that much lower growth. And if we just blindly set this biomass requirement, we're not going to know, like we might miss out on good strategies because we don't know what this here looks like. So we want to identify what the possible outcomes we could get from our engineering strategies before we really set the hardest constraints on our problem. And so to do this, we use what we call production envelopes. Now, I introduced the term now a bit after we actually talk about we've shown quite a few of them already, not only today but also if you recognize this from the last lecture earlier this week. We actually introduced these when we're talking about when we're showing these metabolic pathways and how the solution space really adapted to the knockouts we did. And so essentially what these production envelopes tells us is that they tell us upper and lower bounds for the metabolic objective given a certain cellular objective and for a specific mutant. And that is essentially just a projection of the solution space for our whole cell, and which is originally many dimensional, into two dimensions, specifically the seller objective and the engineering objective. Now you could, in theory, identify them by simply building the solution space and projecting it over. In practice, that is not the best way of doing it. Essentially, what you will do is you will scan over the biomass production, and then for each possible value of this, you're going to do FVA on your engineering objective reaction, and that will give you, for that specific rate, an upper and a lower bound. And that is essentially what we did last time with this sort of simple naive approach, was that where we just brute forced our way through, was we did that FVA for the engineering objective at the cellular with the cellular objective bounded to its optimal value. But we can also do it for all possible values of the cellular objective, and that will give us a more detailed overview of what our possible fluxes are. In practice, the way we're going to do it is we're going to do this on a computer, so we can't really just plot out a function. What we're going to do is we're going to have a quite finely resolved set of specific points, say for instance every 0.01, and so we're going to set biomass fixed 0.01 FVA for lactate production, biomass 0.02 fixed FVA, and so on. And then for a certain number of points, we can get it quite finely resolved in a respectable amount of time, and then that will allow us to essentially draw out our lines here. And these production envelopes, they have various uses. The first is that it allows us to see, for the optimal solution, whether it is whether the optimal solution forces production of the engineering objective. Because for OpNoc, what we can get is that we can have a mutant where the cellular objective and the metabolic objective, the cellular objective and the engineering objective are decoupled. That is essentially what we have here, and that is undesirable. So by doing our production envelopes, we can identify we can identify whether our knockout is actually ensured to produce the objective. The second thing that it gives us is it gives us a level of robustness to our knockout. So for instance, if we look at this mutant C here, no, sorry, this is actually mutant A. If we look at mutant A here, it has a pretty high growth, or it has at its optimal growth, it has a pretty high production, and that is guaranteed if the cell is optimal. But then again, we don't necessarily have a cell that is strictly optimal. A cell that grows at 97% of the optimum can still be considered generally quite competitive, and that would give us a bit of a problem here, because what we see here is that, sure, this point here, if we just did FVA on the optimum, we would find ensured production. But if we slacken our FBA constraints a little bit, our FVA constraint a little bit, then suddenly we are no longer guaranteed to have production of the engineering objective. And so the fact that this here is a very wide angle is also something that doesn't look too good for this mutant A. Meanwhile, if we look at mutant B, we can diverge quite far from our optimal growth and still have an acceptable production of the engineering objective. And so the nice thing with our production envelopes is that it gives us a good overview of how reliably can we expect our mutant to produce the desired metabolite. Similarly, or further, production envelopes are sort of related to phenotype phase plane and to the robustness analysis curves, but they're a bit different as well. There's some overlap there, but I'll explain that in detail or somewhat more thoroughly in a few slides. The last thing that we can use the production envelope for is that the production envelope for the wild type essentially gives us more or less of an indication of what is the best result we can expect to get from a mutant. So yeah, okay. So I actually ended up talking about phenotype phase planes before we talked about that last bit. And so on the right here we have a phenotype phase plane, and on the left we have a production envelope for just one variable. So essentially what this phenotype phase plane corresponds to, or in this case on the left, on our production envelope we have two variables. This is two-dimensional. We have our lactate production, and then we have our biomass production. Now we could essentially introduce a third variable. Suppose that we want to engineer our cell to produce two byproducts at the same time. Now, from an original optimization problem, it's a bit trickier. But what we could do is we could plot out this production envelope in 3 dimensions. So instead of this shape here being bounded by a line above and below for a given rate of biomass, we would have a surface that projects, probably at an angle, if it were any interesting, into a theoretical third dimension. And so that would and then it would really be like a literal envelope. You would have an area of space bounded by a plane above and a plane below, and for that matter also on the side here, since the biomass production is irreversible. And what we would have in this three-dimensional production envelope, we would have this upper bound and the lower bound, and the upper bound would then be the same as our phenotype phase plane, because that is essentially what's being told here, right? The phenotype phase plane shows the maximum growth, that would be this, at a fixed rate of glucose uptake, or uptake of metabolite 1, and fixed uptake of metabolite B. Another slight difference here is that here we're using uptake rates as axes, and here we're using secretion rates. That seems maybe like a useful or an important distinction, but it really isn't, because secretion and uptake are essentially the same thing, just in a reverse direction. It's just that in practice, when we're doing phenotype phase planes, we're usually mostly concerned about environments, which are reflected by uptake rates. And in most metabolic engineering problems, we're after secretion of a product. There is nothing preventing you from doing a metabolic engineering problem where you want to engineer your cell so as to uptake as much as possible of a certain metabolite. Suppose if you want to engineer a cell to do some sort of cleanup for oil spills or something of the like, that would be a valid engineering objective. Just that in real life, those problems don't occur that often. But the x-axis here is really the same type of reaction as we have on the y-axis here. If we remember the discussion from phenotype phase plane, we could do this sort of robust list analysis where essentially we would take slices. We would, for instance, fix our nitrogen uptake rate at 6, and we would take a slice of this curve here, or of this surface here, and that would give us just a curve that is in 2 dimensions seen from the side. Those should not be confused with these lactate production limits, because when we're doing robustness analysis, we are fixed at a point here. We're not allowed to move further in or further back in any other coordinate. Remember that this here is not the entire solution space. It is a projection of the solution space in 2 dimensions. And typically the solution space for a real case would be, for instance, constrained here between 4 and 0. And so if our uptake rate would be bound at 4, our production envelope for glucose, or uptake envelope, I guess, for glucose, would not be this line here going off 4. It would be what we saw looking at the origin from sort of this direction, and what we would see first here. So the upper point here would essentially correspond to this edge. And this edge, as you can see, moves in along this axis. So this might be a little bit confusing, but the point being that if you were to do a two-dimensional phenotype, a two-dimensional production envelope, the upper half of it, the upper bound of the surface of the production envelope, would be the same as a phenotype phase plane, because what you're doing is then you would be constraining both metabolites at once. But if you're doing it, essentially what is the single variable version of a phenotype phase plane, which is just this robustness analysis, you are locking this variable, which is not something you're doing in the production envelope. So two-dimensional, they're very similar, but one-dimensional, or if you have two variables plus 2 dimensions plus biomass, they're very similar. If you have 1 dimension plus biomass, they will be very different. And so the last thing that is useful that production envelopes are useful for is identifying sort of the best case we can get from an engineering perspective. So this here is sort of a slightly modified recap from what we had in the previous lecture, where we have our pathway. We have here these lines without coloring, and show the original model, and then red show what we knock out in our mutant. And so our wild type, which includes the red lines, will have a solution space that looks like this, something along these lines. Meanwhile, our mutant will have a solution space that looks more like this here at the bottom. And initially, one would think that these aren't too similar at all, or this here doesn't really tell us anything about this here. But what is important to keep in mind is that as we do knockouts, all we do is we narrow in the solution space. And since the production envelope is essentially a projection of the solution space, we'll also narrow in the production envelope. If this is your starting point, this production envelope here, you're never going to be able to do a mutant that brings you outside of it. And so even if this here looks like it would start somewhere else, this is just because the axes are relabeled. In reality, this shape here corresponds rather to something like this, which you see, this area here is strictly contained within our original production envelope. And so therefore, before we start doing our metabolic engineering strategies, or looking for metabolic engineering strategies, doing a production envelope for the wild type can be very useful, because we might just be able to identify that this wild type here is not valid, that this wild type has no scenario in which it will produce any respectable amount. If, say, our envelope, instead of following here, was just down here the whole time, no matter which mutant we tried, we get something that is as effective, or efficient enough in satisfying our engineering objective. And so with that phenotype phase planes are quite useful in setting a baseline for what we can expect from our strategies. Because ideally, what we want to do is we want to identify mutants that lie along the upper bound of this, somewhere along this upper curve of our of our original production envelope. Because we can't do better than it, so what we want to do is we want to just find as close to it as possible. So yeah, that is a summary of production envelopes and what they're useful for, what they tell us about the capabilities of a cell, and why when we're doing metabolic engineering, even if we're doing it simple, but especially if we're doing it through more complicated, or through OpNoC, which is has value in that it allows us to search strategies more exhaustively, we always want to use production envelopes to foolproof our knockout, just to get a detailed overview of what really are the capabilities of our knockout. Because if we do OpNoC, we're only going to find this single point here, and that gives us very little information. If we do this, the simpler approach that we showed last time, where we just do FVA on the optimum, will give us a better overview than OpNoC, but it will still only give us, for instance, this line, and that is not necessarily super useful if you, for instance, have something like this, where sure, your optimal solution, or this would actually be caught fine by a single, or by OpNoC, but if you had a certain variation here that was acceptable at the optimum, but just a slight drop from the optimum suddenly loses you that guaranteed production of the engineering objective, that is an undesirable case. And so even if you do FVA in the optimum and you ensure yourself that, oh, this is a safe optimum, if you don't do the whole production envelope, you can't be that sure, because in real life the cell won't be strictly optimized. It might behave somewhat less optimally and still be able to stay competitive enough in the large scheme of things. So yeah, that is I think brings us up to speed on the key aspects of metabolic engineering. Generally, like looking the strategies for identifying knockouts that produce, or that allows our cell, or that rather forces our cell to produce something we desire in order to satisfy its own objectives. Alright, I think that's it for today.